Great. Okay, so I guess I'll start over, but all the amazing proofs that I did in the last 5 minutes, I'm not going to do them again because that took, we don't want to do things twice. So I actually did the Riemann hypothesis, which has nothing to do with what we're proving today. So I'm so sorry, but there's some guy in the chat who's got it. So maybe just reach out to that guy. Okay. Anyway, I'm Nannah. I'm a grad student here. I'm not a grad student somewhere else. That wouldn't make any sense. But yes, I go to school here. And I lost my piece of paper. There it is. Okay, back to what I was saying. On the labs that I teach on Thursdays, all of my students created this class norm that I have to open my labs with a horrible dad joke that relates to math. So in this particular section, I know you guys just went through this with Alec, but we're going to talk about choose functions. And if there's anyone in the world that I would want to spend 24 hours learning math with, I choose you. Wow, that was so funny. Nannah, you're such a great jokester. We'll have more of those, unfortunately. Okay. Michael, you can move forward. Wow, I cannot see that. Okay, thank you. So recall, and by that I mean from 5.5 minutes ago, when Alec was telling us about the number of ways to choose k objects without repetition from a set of n things. So if I have a set of n grad students and I only want k of them to run math day, we can do that with this. So it's also, I think this is the same thing. Alternatively, n choose k is the number of k element subsets of an n set, and it's read as n choose k, or I choose you. Okay, thank you, Michael. Where are we? Okay, oh, this is great. It's perfect, and I've lost my pen. So again, pretend like you didn't learn this because we're still going to go over it. The number of ways to choose n objects from k is given by this. So we get n factorial, k factorial, and then n minus k. Someone remind me, what is factorial, except just this looks like we're really excited about letters, but what does it actually mean? Nice. Sweet. Okay, cool. Thank you, Hannah. Great. And I could prove that this works just by doing exactly what Hannah just said. So we've got this, n minus 1 times n minus 2 times n minus k plus 1 is equal to this. Oh, geez. How do we feel about that? Pretty good? Awesome. Good enough to give myself a QED?
I would not choose that.
Okay. All right, continue forward, please. Okay, so we have a fun problem to do. An old Hungarian bus ticket has 9 squares and is validated by punching a punch machine. And that makes a number of holes in this ticket. And if you want to avoid paying a fare, you can choose possible valid tickets. So does that make sense? You don't want to pay for the bus, so you just make your own tickets at home. How many ways can we do that with, how many tickets do you have to need to have all possible 3-hole tickets? Nice. We're going to do it. Oh, whoops. And how did you come up with that fun little fact? Out of 9 total. Yeah, awesome. Okay. Quick in your head, what does that equal?
9 choose 3.
Thank you. All right, we get this, and then 3, and then this is 6. Did I do the work? I did. Okay, so then we get 9 times 8 times 7 times 6, blah. 3 times 2 times 1, 6 times, and I'm just gonna go like this. Are we okay with that? The blahs cancel, exactly. We end up with 9 times 8 times 7 over 6. And I'm super good at math, and quickly in my head, without looking at my paper, that is 84 possibilities. Awesome. Okay, so that's 84 ways to make a 3-hole ticket. So if you don't want to pay the fare, I hope you have a lot of time on your hands. And then our part B, what about 4 and 5 holes? They're the same amount as each other? Wow. Let's prove it to ourselves. Okay, so 9 choose 4. That gives us 9 factorial. 4, right? Yeah, 4. And then, thank you. Okay, stuff cancels. And we could do it, or I could just tell you 126, right? Okay, so that's 4 whole tickets. Okay, and then you told me, someone in the crowd said, hey, this is gonna be the same thing, but let's do it anyway, just to be sure. 9 choose 5, we get 9 factorial. That's a 5. 5, 9 minus 5. Here we go. And this is 4. What do we notice?
About 126.
Multiplication commutes.
Wow. You think this would be about 126? I agree with you. And this is for the 5 whole ticket. Why? Like, just like, would we just like stumble upon something super fun in math that we created today, or is this like a real thing?
Real thing.
Real thing? What does this even mean? Okay, so I heard you can choose or you could not choose.
Choosing something, you're automatically not choosing what's left.
Exactly. So my joke earlier when I said I choose you, I'm automatically not choosing the rest of the world. So you guys should be very special. Okay, cool. So this is actually going to lead us to a really exciting thing called the complement identity, which will be on the next slide. Oh, look at that. Thank you. And that tells us we have n minus k is equal to n choose k. We could just like believe this on faith, never prove another thing in our lives, and end this right now. Or we could do it. Okay, we know already that this one is n factorial, k factorial, n minus k factorial, right? That's over here. Okay, and this is going to be equal to now this side. Here we got this. I mean, these look pretty similar, right? Right? No? I think they look similar. And so done, there's one proof. I think it'd be really fun. I found this other proof online that shows doing it through a bijective function, which I would not have thought to do. So that's pretty cool.
N minus.
Yeah. Okay, I think we should do it. But I have to remember how to do it. Okay, so we're going to show a bijection between 2 sets. Set 1 is going to be, whoopsies, n choose k, and set 2 is, is going to be n to the n, or choose n minus k. And since there's a bijection here, they have the same cardinality, so that's very cool. So we're going to let P equal, P is going to be the set of k elements. And where am I? Then the size of P, or the cardinality of P, is equal to n choose k. Does that work for you guys? Cool. Is that right? Yeah, cool. Okay. For example, just like show this bit, if I had n equals 4 and I had k equals 2, then I have P equals this set here of, like I got 1, 2, and I got 1, 3, and I got 1, 4. I regret writing all this down. 2, 3. There's more options. You want me to keep writing them? Okay, cool. What was that? Okay. Okay, cool. I like it. So what is the size of P? We got 1, 2, 3, 4, 5, 6. Awesome. Okay, now we want to note the complement in that's a square bracket with any A contained in N. And using this example, that would be like 1, 4 is contained, oopsies, in here. I think these are supposed to be the same. Is that what I'm trying to say? Yeah. So then we have this. Awesome. Okay, now we need, I ran out of room. We'll just go up here. Let Q is going to be the set of n minus k. And subsets of this. Okay. How are we feeling? Is that okay? Okay. I unfortunately need to erase this because I ran out of room. Is that all right with everyone? If I prove this twice, do I get 2 counts? But I mean, like, I did the work. Okay. That's an F. Okay, we have our function. We're going from P to Q, which was mentioned earlier. And it's a bijection, so we have to show 2 things. 1, onto, and 2, 1 to 1. And we'll do onto first, which seems, I usually do 1 to 1 first, but that's okay. So onto, given T and Q, then S is equal to T here. And this satisfies it, right? So we just plug this bad boy in there. We got this. I think I need one here. Yeah. Awesome. And we got this. All right, so we have the order of S is equal to N minus the order of T. And then this is also, oopsie, this is equal to N minus K, which is equal to K. Yay. So S is contained in P. And then 2, 1 to 1. We got if F of R is equal to F of S, then this is going to tell us that our complement is equal to S complement. And we got wrong way. Which R equals S, which is what we wanted to show for 1 to 1. Yay. Therefore, we have a bijection, and the cardinality or order of P is equal to the order of Q, and we're done. I like it. Yeah. So I get 2. Well, except they're equal, so I only get the 1. Okay. Are we on? Okay, thank you. We have another really fun identity. This is called the chairperson identity. Essentially, it tells us we have a bunch of people, and we choose to put one of them in a chair. I'm just kidding. That's not actually what it's called. Yes. Yeah. I think we just want one of them on a chair, in fact. Pardon? Okay.
We have some subset of people and only one of them doesn't.
So this is the complement of the chair identity, the not chair identity. I think they would be called the stand person. Okay, that tells us we have n times n minus 1, choose k minus 1, which is here. And choose k. Okay. So to help my self kind of wrap my head around this all over again, it's been a long time since I've done it. I have this a little fun story. So imagine there's a Nobel Prize being given for the best looking chair. It's probably not one in this room. So we need to establish a group of people of size n who will judge said chairs, with one person who is solely in charge of those judges. So we have a bunch of judges, and then we have someone in charge of the judges. I don't know why we have a panel of judges when one person is in charge of judging those people, but it'll work. So we'll call that guy the chairperson, and we're gonna call him K. And then so on our left-hand side, we have n times n minus 1. So choose k minus 1. And this is the whole group of n people. So from group n, we need to choose exactly one person who's our chairperson. And we're going to choose him first. So yeah. And then over here, after we choose our chairperson, then we're going to create a panel of judges with what's left over. Okay. And then, so this is the left-hand side. And then the right-hand side, we have, just to rewrite it and choose K. So we chose our chairperson first over here, and then we chose the judges of people left over. What do you think we're going to do on this side? And then, nice. Choose judges. I don't have to spell judges anymore. That's okay. And then we'll choose our chairperson. Okay, cool. So eventually this will all allow us to choose our judges and our chairperson. Either you choose one first and then the other, or you choose the other and then you choose the one, and they end up being equal to each other. Okay? Okay. Okay. Thank you. So we could do a quick example here. So we have we don't need this. We have a group of 5, so n is going to equal to 5. And then we've got n times, 5 times 4. And then our group size, what do we need our group size to be? I need to read my notes. Oh, 3. We want 3, our committee to be 3 people. Okay, so then we do 3 minus 1 here, which is 2. And that, if we did a bunch of algebra, that's going to be 30. Or we do the other way, where we choose 3, or we have 3, and then we do 5, choose 3. And we can do a bunch of algebra, and it turns out that also equals 30. Is a great example. Yay. Okay. So I feel like this wasn't really a proof. It was just kind of explaining things. And I want the QED count, so we're going to suffer through this for a second. Oh, oopsie. Okay, so we have n times n minus 1 factorial over k minus 1 factorial, and then, oh, this is going to be brutal. Okay. Oof. And then we get this again. Okay, and then we can cancel some stuff, which is very exciting. So that looks like it can go away. We'll get here. This doesn't seem quite right. Oh yeah, this, okay, great, we're good. Okay, awesome. And then on the right-hand side, we have for this, I'm gonna pull out a K, and then we can do some canceling. And also an N. Okay, that goes away. And then I think we can get some other stuff out of here. No, we're good. Okay, and this is, we ended up with the same thing, which is very exciting. Yay, QED. Okay, we can keep going. Okay, we're continuing on our identity theorems journey. So now we have a subcommittee theorem, which essentially says if I have a size of n people and I want to make a committee of k people, and then I actually, like, within that committee want a smaller group of people, we'll call that R. So let's see, we got two M's, one M, doesn't matter. Awesome. Okay, so we have two ways to build these, and they are going to be equal to each other. So for the left-hand side, we get, it's right there. This says, first, we're going to choose our larger, like, regular committee. And then after that, we're going to build our subcommittee. Of size R. Okay, and then on the right-hand side, our other option is to first build the subcommittee. And then from our smaller committee, we're going to choose more people to make our bigger committee. Okay. And turns out, no matter what order we do this, we can either do this first or we can do this first. And we get the same amount of choices for each. Yeah. Cool. I want to do a fun example for this. So like let's let n equal 8 and k can equal 5 and r can equal 3. I gave it away. And I want to show that 8 choose 5 and where's my r? 5 choose 3 is the same as 8 choose 3. And then 8 minus 3 choose 5 minus 3. Okay, so 8 choose 5 is here. And then 8 minus 5 is 3, so we'll just go like this. And here we got 5 choose 3 is 5 factorial, 3 factorial, 5 minus 3 is 2. And we don't know this yet, but we kind of do. 8 choose 3. Oh, so 8 minus 3 is 5. And then we've got 8 minus 3 is 5, that's 2, right? Yeah. Am I doing this right? Thank you. And 3. Do we believe it yet? Or should we keep going?
I mean, I believe it when it popped up on the slide.
Sure, fair. Okay, so after some fun algebra, this is 56, and this is going to be 10, so that's 560. And this is going to be here, right, 56, and this is going to be 10. And now we believe it with our whole heart. Yay. Okay. We are cruising. Okay, another theorem. This is the sum of binomial coefficients. And we want to show that n choose 0 plus n choose 1 plus n choose 2 plus ... n choose n minus 1 plus n choose n is going to be to some exciting number 2 to the power of n. Okay. I don't like that. Let me catch up real quick. Okay, so we have a set of n, and we want to know the total number of subsets. And we went over this earlier with Alec, but that's okay. Subsets can be any size, ranging from like 0 to n. So if it's 0, that subset doesn't have anything in it, but it still counts. And then if it's a subset of size n, that's the subset of the whole set. We still count it. So it's very exciting. And just for like fun notation, if we have n choose 0, like I said, subset of size 0. And if we have n choose 1, what's the subset size of this one? Nice. And then this is the whole set. Okay, great. Okay, so for each element in the set n, there are two options. You're either in the set or you're not in the set. Okay? Sorry, in the subset or you're not in the subset. So since there are n elements and each element has two choices, we end up with two choices per element to be in or out of the subset. So then that will tell us that n choose 0 plus n choose 1 plus, where are we? N choose n minus 1 plus, oopsie, here you go, n choose n. If I have n amount of subsets with 2 possibilities, we do in fact get 2 to the power of n. And a fun little example, let's see, let's let n be 4. When I was working on these, I was like, oh, let's just pick like 5, and then I remembered that that would take forever. So even 4 is gonna suck, but that's okay. So we have 4 choose 0, plus 4 choose 1, plus 4 choose 2, plus, I really wish I would have done 3, 4 choose 3, plus 4 choose 4 is equal to 2, I guess, well, we already know, 2 to the power of 4. I think that's 16, right? Sweet. Okay, 4 choose 0, what's that? What's that, Hannah? Oh, it's 1, okay. 4 choose 1, what's that? Nice. 4 choose 2, what's that? Oh, no more hands in the air. Oh, okay. Yeah. 4 choose 3, what's that? Nice. Do we see a pattern here? Wow. Am I here? I'm here. 4 choose 4, how many options, or how many ways can we choose 4 subsets of size 4? 1. This is really cool, by the way. I wonder if that's just like random, or if that'll pop up in our near future. Anyway, 4 plus 4 is 8, plus 2 is 10, plus 6 is 16. We got 16 equals 16. Super exciting for us. Love to see it. Well, that was an example, but I guess I'll give myself one anyway. I did, yeah. Thank you. Could you imagine if I said, let's do an example, let's like let n be 50. We'd be here all day. Yeah. Corey's like, I need to like sleep a little bit more. I'm like, all right, we're doing examples and choose 1,000.
Better.
Yeah. Okay, so now we have the middle binomial identity. Any other middle children out there? This one's for us. You know, when your siblings are born and your parents like, oh, what a nice little older binomial. And then you're born and they're like, oh, what a nice little middle binomial. Yeah. Okay, so this is gonna say, we have, here we go, I'll just write it first. To n choose n, okay. So on the left-hand side, we have the sum of n choose I squared, and we're running over from n to I. And then on the right-hand side, we have 2n choose n, and somehow we have to show that these are equal to each other. Any wild ideas? Yeah, I think that's actually what it is. Okay, so this, oh, yeah, I already told you that. Okay, never mind. So now, just to like put it into real world context, consider a situation where we have 2 sets of size n. So one over here, one over there. And we want to know the number of ways to select n objects with unique, sorry, I'm going all over the place. And we want to know the number of ways to select n objects from the union of set A and set B, my 2 sets. Each of them have n objects, and then we'll end up with A union B is going to give us, where am I? 2 times n objects. And then the number of ways to choose from A is going to give us n choose I. Yay. And the number of ways to choose the remaining elements from, remaining n minus I elements from set B is going to be, in fact, where am I? N minus I, which is actually, as we just found out, equal to n choose I. Wow. Okay, we'll do a fun example again. Let's let n equal 3. I learned my lesson from last time. So we have the sum of I equals 0 to 3, and we got n choose I squared equals to, oh, not n, it's equal to 3. And 3. So over here, we have 6 choose 3. And over here, we have 3 choose 0, square it, plus 3 choose 1, square it, plus 3 choose 2, square it, plus, everyone with me now, 3 choose 3, square it, woo! Okay, what's 3 choose 0? Nice. What's 1 squared? Nice. What's 3 choose 1? What's 3 squared? Love to see it. Excuse me, what's 3 choose 2? Said it with confidence. And then I know everyone knows that that's 9. What's 3 choose 3? 1 squared is 1. What did you say? Yeah. What's 6 choose 3? Well, let's try. Okay, so what's 9 plus 9 is 18. Add 2, this is 20. And it is indeed 20. Yay! Very exciting for us. No, we're going to prove it. Oh, am I? I don't know that we are actually going to do that. What did I do? Give me 1 second. I must have been really tired when I wrote this. I wrote 2 examples, and I don't think we need to do that twice. Okay, I think we're okay. I think it's pretty good. Yeah. No, I don't want it.
know when the sun rises?
See you in the morning. Your rises is about 2 o'clock.
Is it every day in the morning, or like sometimes we don't really see it? That's fair.
The evening apparently is rising real late. It's
Night was so long that we're.
Has anyone ever seen Singing in the Rain? There's a whole like song about that. Good morning, good morning. Sorry. Okay. Pascal's identity tells us that n choose k is going to end up being the same thing as n minus 1 choose k plus n minus 1 choose k minus 1. So we have a set, it's double counting, like we said earlier, sets of size k of an n element set. So here we go. We're gonna, this is funny, I don't think it's gonna count, but we're gonna fix an element. And I called it pi just because I thought it would be like Pi Day stuff. So in this case, pi is not a number, it's an element. So if you get confused, we can switch it, but I think that adds here. 1, 2, 3, 4, 5. Yay!
You know.
Is a piece of pie really pi? Okay, I'll do that. I'll be up here writing decimals forever. Okay. And it's in an n size set. Very exciting. So then we want to find the number of sets of size k containing our element pi. And that's going to get us to here. Okay. And because we already picked one, we have n minus 1 sized sets containing k minus 1 elements. So then consider the sets of size k without our fun little pi, and that's n minus 1, choose k. Because there were n minus 1 things that aren't pi, and we need k elements in our set. Cool? So then we end up with our identity. Yay. So now, if we want, we can prove it by double counting binary strings of lengths n with exactly k ones. And a binary string is like ones and zeros. Yeah. Backwards and forwards. Okay. So we'll have, where am I? N choose k be the number of binary strings of length n. Okay. So we either have a 1 or we have a 0. Got it? All right. So then we're going to choose k1s first. And that's going to give us the number of strings starting with 1. Because if we chose 1 first, our string starts with 1. And our pool, like what we can choose from, is now limited to n minus 1. Okay. And then since the first thing is a 1, we have k minus 1 options. And we want to, let's see, now we need to start with 0. So this starts with 0 instead of a 1. So we have n minus 1 places to put other options. And we still have k options left. So k numbers of 1. Yay. Do you have any questions? Great. I think so.
Yay.
Yeah, so I like all my proofs end with yay instead of the box. I just think it's more fun. What? Y-A-Y? Is there an option to do an E? Oh, okay, okay. No. Okay, now we're going to talk about lattice paths. Has anyone, well, maybe I don't know if the age group is here, but did anyone grow up with PBS Kids? Okay, same. Did you guys watch Arthur? Okay, so then also when computers became a thing in our childhood, there's this fun game on pbskids.org/games, and DW, which is Arthur's little sister, has to find a way from her bedroom to the bathroom to get a glass of water without stepping on baby Kate's, that's Arthur's youngest sister, like her toys. We don't want to wake up baby Kate. And somehow, for some reason, DW can either walk like this or like this, okay? And there's like things in the way. So if I walk this way and I'm DW and I step on something, baby Kate just woke up and game over. So essentially, that fun game that we all played maybe when we were like 7 is an example of a lattice path. And if only we knew. So a northeast lattice path is a path from 0, 0 to a point MN. we're gonna go like this. So I'll put 0, 0 here, and we're going northeast. So I guess this is northeast here. And we can only move up 1 or over 1, right? So if we move up, we did 1, 0. And if we move over, we did 0, 1. And we do this to get to here. Alrighty. So if that wasn't clear enough, what is a lattice path? It's a path composed of connected horizontal and vertical line segments, each passing through adjacent lattice points. Let's see, we can only go north and east. So how many ways can we go? Let's call this 3, 3. Any ideas? How many ways, like, can we go up, over? How many options can we go? I'm sure there's something. Yeah, do you have an idea? Okay. Okay. Cool. So particularly for 3, choose 3, we have, I want to know the number of paths to go from here to there. And let's try this one. So we can either go like north, north, north. So we go 1, 2, we'll call this 2, 0, and then 3. And then because I did this, our other options are to go 1, we'll call this 3, 1, 2, and then 3, 3. Okay, so that was north, 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 east, east, east. But that's not the only option. What else can we do?
East, north, east, north, east.
Okay, cool. So that's going to be north, east, north. Oh, I think I need to go bigger. North, east. So we did north. No, we did east and north and east and north. And I think I feel like I should have made it by now. We'll get there eventually. Yeah. So essentially we did north, east. Oh, my example is different than what Michael suggested. We'll do mine first. We do north, and then we go east. Oh, no, no, this is horrible. Here we go, north, and then east. So that was north, and then east. Okay? And then for chaos, we go north. Then we go north again. This is 1, 2, I think we're up here now, right? Yeah, so that was north again. And then what are my options now? East, east. So that was north, no, that was, yeah, thanks, sorry guys. North, east, north, north, east, east. But as Michael just suggested, we actually have another option. You want to tell it to me again? Northeast, northeast, northeast. Stop yawning. I don't want to drive. Is there another option? Hannah's got a problem with this one. Okay. And oh, that was 10 years ago. Okay, so we actually have, we can like show how many we have with this. We have 3 options to go north, and then we have 3 options to go east, and we're gonna choose 3. So 3 plus 3 is 6. Choose 3. Sorry. Okay. I already forgot what 6 choose 3 was, but that's a number. Love it. Okay, so in general, to get to a point somewhere on here, the number of paths or walks or Euler's tours, I guess. I think, yeah, from 0, 0 to, we're gonna call this K and N minus K. So K is north, moves. And this is gonna be east moves. Interesting. Okay. No.
I'm not seeing that.
She emailed me.
Okay, so I'm,
Let me check.
yeah.
Oh, we're good.
We're good? Okay. Okay, maybe she emailed you like an hour ago and it's just now coming through. Wow, okay. Okay, so then in relation to Pascal's triangle, which we talked about, that was n choose k is equal to n minus 1 k, choose k, plus n minus 1 choose k minus 1. So if I choose to move east first by 1, then I have n minus 1 spots for other moves. Okay, so that's where this comes in. But now if we want to start with a move north, then we have n minus 1 moves left, but we still have k options to go east. So that's where we get this one, and therefore we can actually figure out our last paths using Pascal's identity. Woohoo! That's so exciting. I'm not being sarcastic. That was really exciting. Okay. I have a note to myself. Okay. It says slide 13 is just showing Pascal's identity, and the identities we will be proving. Is that right? Okay, let's go to 12. Can you go back one more? One more. Okay, so am I crazy or is that the same thing? Okay, so let's go forward 2. QED twice. Listen.
It had double counting.
Yeah, and we're counting it twice. Okay.
Here's what I'm thinking. When you've got it twice, you can prove it one way. So how about 2 choose 1 through these?
No. Okay. Can we move on to the next one? Oh, I gotta erase.
I assume you need more than this for the next one.
No, hang tight here. Yeah. Okay. Have you guys ever seen Tangled? The Disney princess movie? Okay. Question for you. What is Rapunzel's favorite triangle? Pascal's triangle. Why? Have you ever seen Rapunzel? Her chamomile is named Pascal. Wow, Nannah, you're so good at jokes. Okay, this is Pascal's triangle. It has nothing to do with chameleons. But it's super cool, and we can do a lot with it, and I'm actually really excited about this. So it looks like a triangle, step number 1. And then if we're looking at it, we've got like a lot of different colors going on here. That's just because I was bored and needed to like color some things in. They have nothing to do with the rest of this talk. No. Okay, so can you go back? Thank you. Okay. I'm gonna build one here and it's gonna hang tight. We have, can you make it big again so I can look at it? That's okay. 0, 2, 0, and then we have, what is it? 1, yeah, 1, choose 0, and then we'll have 1, choose 1, and we have, oopsie, 2, choose 0, 2, choose 1, 2, choose, whoa. 2, choose, 3, choose 0, 3, choose 1, 3, this is hard, 3, choose 2, 3, choose 3, and we'll do one more for fun. 4, choose 0, 4, choose 1, 4, choose 2, I can't count, 4, choose 3, and 4, choose 4. It's just slow. Okay, thank you. You can switch it back. Do we notice any patterns happening here? Or is it just a bunch of stuff on a triangle? Yeah, what's up? Got one all the way down? Okay. on this side and that side. So it's almost like 1, 1, 1, 1. What should I put here? Question mark? We can do question mark. Or we can think, yeah, that's fair. Okay. Okay, yeah. Yeah. I think I'm comfortable with it too. Let's do another 1. What do you guys put here? If we're going right here.
3, choose 1.
Okay. What do you think about right here?
2.
Got 2 things happening. 3, 2. What are you doing? No. Okay, that'll be another 3, and then a 1, and I ran out of room. But if you would like to believe me, it'd be a 1, and then a 4, and a 6, and a 4, and a 1. Pretty cool. Okay, now we can keep going. I don't know how to pronounce this person's name, and I feel really bad about that. I'm going to go Erdos. Okay, and this theorem says in any row of Pascal's triangle, any 2 numbers besides the ones have a common factor. Why do we say besides 1?
Because 1 isn't prime.
Okay. Okay. Let's see. Can we do it, like, can we just pick one here and find an example that works?
I think the 3's and the 1 and the 2.
Okay. Common factors.
I mean,
2
there's
has
not.
common factors itself.
Should I do another row?
Yeah.
Would that be easier? We got 1, 4. Yeah. Okay.
2.
Awesome. Okay. Great.
No,
You're good.
you're good. 2 must be.
Do you want me to do another row? We can prove it to you. Okay. It might. Yeah, that's okay. Okay. Oh, I actually am going to do another row. 1, 5, 10, 10, 5, 1. And my example that I've written down is we're going to do row 5. So we already did, yes. Yeah, okay. Yes. The common factor is 5. Awesome. Okay. That's the first time I've written on my board like that. We're going to let N choose what I have here, S. And N choose T. Be the 2 number of ways, sorry, 2 numbers with 0 less than, where am I? Yep. Okay. Did we learn an identity we could use to work through this? That's okay. We're going to keep going. We're going to use a subcommittee identity. And that tells us that N choose T and T choose S is equal to N choose S and N minus S and T minus S. It looks familiar, I'm sure. Okay, then we're going to say that the term N choose S divides the right-hand side. So that's that side. So because these are equal, it also has to divide the left-hand side, right?
Glasses.
You're falling down my face. Okay. So it divides this one and this one. And if N choose S and N choose T have no common factor, then what?
Probably.
That was supposed to be a broken arrow. We've got a contradiction. It's supposed to divide two things and it doesn't because they don't have any common factors. So therefore, this doesn't work. Awesome. Did you need this? Yeah. I should be better about that. I'm really bad at that. Okay. That's my note to not panic. Okay. I wrote, I'm fine. Okay, so for context, I wrote slide 17 info here and then slide 27 info here. So they're not in order. And I have a note in here to be like, don't freak out. It's there somewhere. Okay. Okay, we can keep going. Where are we? Okay. Okay, so this one is, where did my paper go? Aha. I feel like they look very similar. Oh, go back, please. No, make me big. Okay, yeah. So then we have this. So for 0 less than s less than t less than or equal to n divided by 2, the greatest common divisor of n and s and n and t, or sorry, n choose s and n choose t is greater than 2, and I can't read that, to the power of s. Thank you. Pretty cool. Yeah, I feel like I may have spoiled this by doing the last one, but that's okay. Recall our subcommittee identity is going to be important again. That's not it. Oh, geez. N choose k times k choose r is equal to n choose r, yes, times n minus r, k minus r. So that was just a friendly reminder. Then the greatest common divisor of these two things, n choose s with n choose t, is hopefully greater than or equal to 2 to the power of s. Okay, using this, we see that the greatest common divisor, do I have to rewrite this again? I do, of n choose s with, it's gonna be really fun, we're gonna use this bit. N choose, pardon? This little bit. Oh, that's funny. So that's a big divide. T choose s, hopefully. I really hope so. Okay, so now, oh, I just did it with an example. Nice job, Nannah. Okay, we'll do it with an example.
Like s is less than t, so n choose s is the number of it counts subsets. So 2 to the s is the number of subsets. I think that would probably be the.
That'll probably be it, yeah. I'm still gonna do the example, yeah. Okay, so GCD of n is this one. So we have 6 choose 2. That's been popping up a lot. And still 6 choose 2. Well, I guess we'll do it this way. T, what was T? 3 choose 2. Hopefully, this is bigger than 2 choose 2. No, 2 to the power of 2. Oh my God, 2 to the power of 2. Okay, oh my gosh, I'm so tired. What is 6 choose 2? I actually don't know that we've done this one yet. It is 15. Good job. Yeah, we'll go like this. Okay. And then we have 15 divided by, what's 3 choose 2? Nice. Oh, I totally messed it up. Whoopsie. We're not quite there yet. Sorry. Okay, that's 15. And then we actually end up with 6 choose 2 times 9 lost. I feel like I did this wrong. I did. This should not be here. Because we're going to use that. Yeah. Okay. So we have 6 minus 2. Choose 3 minus 2. Now this will be here. 3 choose 2. All right, 6 choose 2. We know that one. Nice. Okay, 6 minus 2 is 4. 3 minus 2 is 1, so 4 choose 1. There'd be a comma here. Divided by 3 choose 2. Oh, there should be a 15 here too. Okay, that's a 15. That's a 4. And divide by 3, you said? I think we'll be okay. Oh, you're right. I don't think I need. Yeah. I just need like the 1, right? Wait. That one belongs. 6 choose 2 is 15. I don't think I need this one because that was 4 choose 1. Yeah, go away. Okay. Jeez. What's 15 times 4? 40. And then, okay. So this is 15 and 60, but divide by 3. Nice. Okay. What's the greatest common divisor of 15 and 20? Okay. What did I say? 15 and 20? You told me that's 5, and we want this to be bigger than 2 squared. What's 2 squared? I think 5 is bigger than 4. I could pay, I mean, at this point, I could probably be convinced otherwise, but I'm going with it. We could vote. Okay, everyone, who believes that 5 is bigger than 4? 1, 2, 3, 4. All right. Who believes otherwise?
I haven't seen it proved yet.
Okay.
I think it might be 5 of us who don't think 5.
No, there was 1, 2, there was 3 of you.
Also probably bigger than 5, so there's at least.
Yeah.
Both of them are finite, so who cares?
Okay, awesome. Great, thank you.
QED.
No. Okay. I think we can switch it to the next one. You can leave it big until I'm ready. I wish I left my triangle up there. I know. Okay. I think it was like 5 minutes ago when we were looking at a pretty triangle and had a bunch of like colored in lines. I lied to you. I wasn't coloring. It's important. So the row sum identity. We're going to calculate the sum of entries in the rows of Pascal's triangle. We'll try one of them. We have, let's go 1. We got 1 and 1 and 1 and 2 and 1 and 1. Okay. Okay.
And then I don't know.
5, 10,
You can do it. 1, 5.
10, 10,
Mm-hmm.
5, 1.
Okay, do you want to do another one?
Yeah. 6, 15, 20, 15, 6.
1, 7,
21, 35,
odd ones have.
What about the even ones? Okay. Yeah.
Two ones above it.
Yeah. Yeah. So we could give you a little hint. So we have 1, and then we do 1. There's always ones on the outside, right? And then we add 1 plus 1 is 2. And then we do 1 plus 2 is, so we go 1, 1 plus 2 is 3. 2 plus 1 is 3 and 1. And then what's this one going to be? Right? Yeah. And then 3 plus 3. Yeah.
Okay.
Mm-hmm.
Now we just need to prove it.
No. Next slide. Prove the triangle. Okay, what are we doing? We want to show the sum of the entries in the rows, and the rows are this way. What's the sum of this one?
1,
Nice. What's the sum of this one?
2,
Okay, and what's the sum of this one? No? Yeah. Oh my God. Thank you. That's 6 plus 2 is that 8? And then 10, 5 plus 1. Thank you. What's this one? You're very quick.
Hoping.
Okay,
Better be 64.
let's see. Technically, yes, yeah. What did you say? This is 64, and we're done. It's fine. So, without remembering what we did in the past, without recalling that, just like generally, what do you think is happening here? It's doubling. Okay, so this was 2 to what? Okay, this one was. What's this one? Nice. What's this one?
2 to 4, 2 to 5, 2 to 6,
I don't know.
2 to 7. Got it.
Oh, no. Awesome. That's so exciting. Yeah. Okay, but my next question would be like, what do you notice? What do you wonder? Call back to my education side of life. But I think we got it. It seems to be doubling. Thank you. Does this look familiar? Maybe? Yeah. Yeah. Crazy. Yeah. Who'd have thunk? Okay, so but in like English words, also known as words, the binomial coefficients, which count the number of ways to choose I elements from the set n, is going to be equal to the number of ways to choose things in a set n, which is 2 to the n. Okay. Awesome. I think that's all for this one. Yeah. I think they're just there to indicate we're doing rows, but we could add them together.
Well, no, I mean, it just seems like they.
Entries in the top of the choose.
Oh, yeah.
What's special about that? Ask the number theorist.
But like, if that's the case, why isn't 11 highlighted? Oh, not from this angle. Okay. It looks very gray. All right, cool. Well, I'm glad that happened.
Oh, maybe. Yeah, 2 to a 5.
Hmm.
So that maybe like model.
Yeah. Well, it's okay. We were asked to prove this. I think we already did, right? Okay, so I'm going to count that 4 more times. Because we did it twice, right? And we could do it 4 ways. So I'm going to go 1, 2, 3, 4, and then 1 more for good luck. Okay. Okay. So there's a fun little fact about me that most of you know. I'm from Minnesota, the great state of hockey. And like, go Wild. I'm actually not much of a hockey fan, but go Wild anyway. And we have a really awesome women's hockey team right now. So in honor of that, and for no other reason, we're going to talk about the hockey stick identity. Why do you think this is called a hockey stick identity?
It looks like
Looks like a hockey stick. That's a good one. Okay.
Like L's in the chat.
Yeah, brought to you by Red Bull. Yeah, I'm flying high. I keep erasing my triangle, which is really unfortunate. I know. Okay, wait, do it with me. 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. One more. 1, 6, 15, 20.
15.
Oh God, 15, 6, 1. That looks like a big long number. Yay, thanks guys. Okay, let's find a hockey stick with a different color. Let's go 1. These are hard to draw. 2, and I go to 4. Oh, I need to do this. That way. This hockey stick has seen some bad days. I'll add some tape to it. Yeah. And then we'll do this one. 1, 10. Oh man. Is this gonna be a problem? No. That's a horrible stick. I think that's all I can do. Oh, I want to do one more. Okay, 1, 7, 21, 35, 35. Thank you. 7, 1. Okay. Before we do anything, is there anything that anyone's noticing? Besides, awesome. About hockey, anyone noticing anything?
The line lines up to the little puck thing at the end.
What?
I think if you got 1, 2, 3, 4, they add up to 10.
Ah, yes. Okay. You said puck. This is also, yeah. Yeah, nice. Okay. No, you're good. I love it. This is part of the hockey stick. A puck would be like over here. That's all I know about hockey. So, okay. So you said there was 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. Okay. 1 plus 4 is, plus 10 is, nice. Okay. Did I do another one? No. What else do we kind of notice? It also has to do with adding.
Running down the stick, I seem to be counting by something.
Okay. Let's do something like that we add something in the stick and we get something outside of the stick. Yeah, okay. That's yeah, okay, so we're choosing zeros and then what? Okay. And then what about the top part? By sweet. What else do we notice? I'm noticing that you guys told me this adds to 10, right? What if I add this 10? Do I get 20? That's pretty cool, right? And what you told me this adds to 15. Let's add, scooch that over. Wait, hold on. Oh no.
Error.
Do we have a problem? I think this is an issue. What happened? 1, 5. It should be 35, but it's not.
Well, it's because that hockey stick is bent.
Well, we can use this triangle to like fix it.
Yeah, let's do that.
We're in the 3, 3.
Mm-hmm.
Hockey sticks hits
So
10,
3,
it
3,
should
4,
hit
3,
the other.
5, 3. And did you want 6, 2, 4?
So like, let's do one that's colored, right? We've got all these, and then we got, so now we, like you were told us that this is all gonna be 5, and then we add 1, and then for our choose set, and then we have 5, 6, 7, 8, 9, and we're increasing, right? What do we get here? It's gonna tell us the next one, right? Does that kind of make sense?
The issue that the diagonal stopped being diagonal and went more.
More,
It's the wrong.
yeah.
It should go 1, 4, 10, 20.
Ah. So go here. I stopped too soon.
You guys have hockey sticks? Hockey the other way.
Is that better? Did we do it?
Well, it should go 1, 4. No, I think that's the right 10, isn't it?
That looks good. Yeah.
Okay, then but if we grab the 15 after that 10, which is
We don't want it though.
no, we should grab it.
Yeah. That's yuck. We want 1, 4, 10, 20, 35. Is that good? 10. Yeah, it totally is. 20 plus 10 plus 5. Yeah. Okay. Sorry. Well, could we figure it out? Yeah. Okay. So that being said, we're doing hockey stick. Yeah. So unfortunately, this is not going to look, but you can look on the board over there. We'll do 1, choose 1 plus, I think we're going this way. 2, choose 1 plus 3, choose 1 plus 4, choose 1 plus, sorry, equals, what do you think?
5.
Nice. Okay. Okay, cool. And then I already asked you, please see the patterns. So essentially we're looking at this. We have n choose n plus n plus 1 choose n plus n choose 2. Okay, plus what? I think maybe this is supposed to be an equal sign. Maybe that'll help us. Is that better? We have that here. Oh, I don't know. Well, I have this down here, and I left this blank, so that's great. Yeah. Yeah. Okay. So in general, we're adding these together. That's the sum, right? From I equals 0 all the way to n of k plus I. Choose k. And what do you think we should get on this side? Because we're going all the way to n, right? And then we need one more. Okay? And then I have on here, go women's hockey. Yeah, and that's our hockey stick identity. Yay. Okay. We are going to do a proof by induction for the first time for us. So we're going to fix k and induct on n. So my base case, what do you think it should be? Sure. What do we get for that? Mm-hmm. Bless you.
Bingo.
Thank you for going so fast. Okay, we had this. Nice. And we got 1. Awesome. Thank you, Hannah. Okay. And I think I'll get rid of this bit. Then we get I equals 0 to n, k plus 1, choose k, whoops, equals to, k.
Mouse pen looks like.
I messed this up. Okay. What are we doing now? Here's my sigma. And then we're going to do another one. K plus N plus 1. K. And this, by our inductive step, we get K plus N plus 1. Choose K plus 1 time, or plus, whoopsies, K plus N plus 1, K. Okay. I'm running out of room. Do you guys care if I erase the base case? Okay.
Knocked over the first domino.
Yeah. True. Now they're. So now I'm going to go to K, or to N plus 1. And we have K plus I. Choose K equals K plus N plus 2, K plus 1. And by Pascal's identity, do we need a reminder? It's going to be, never mind. We get K, sorry, N choose K. I think that was what this is a reminder. N choose K. That's equal to N minus 1 choose K plus N minus 1 choose K minus 1. Oops. Okay, so that's our identity to remember. So we are going to end up with K plus N plus 1 choose K plus 1. I'm concerned. K plus N plus 1. And then we get this. And we're going to think of this as like N minus 1. Is that what we wanted? Yeah, that's concerning to me. Yeah. Okay, what were you saying?
Yeah, you get what was on top. You get K plus 1 and then K plus 1 minus 1.
Yeah. Great. Yay. And that's, well, I mean, like we don't want to do like factorial. That'd be confusing. Yeah. So I'm thinking, yeah, QED. I don't know to what you are referring. I feel like I should leave that up. I think I've learned my lesson. No, I don't. Okay, can we go forward? Did you already do that? You did. Dang it. All right, we're doing it again. We're going to be really good at this. It's great practice. Yeah. like we go way back as in like starting at 4 a.m.? Yeah. Oh, wow. Okay, let's do it.
1, 1, 1, 1, 2, 1,
1, 3, 3.
3.
We gotta get in the rhythm.
Yeah.
1, 4,
6, 4, 1, 1, 5, 10, 10.
Ooh, I regret that.
5,
5, 1,
1,
15,
20, 15, 6, 1.
That was beautiful. Okay, so we have that there. Part.
We were this close to being in whole. Like we can't repeated numbers to 3, 1, 4, 1, 5.
Okay, let's talk about Fibonacci. Fibonacci numbers. What is that? Does anyone remember what that was? Have we talked about those today? Yeah. Okay, that was like 4 days ago. So yeah, it's gonna be like a number, yes, a recurrent sequence, and our numbers are gonna be given by f of 0 equals 0, f of f1 equals 1. What's f2? What's f3? Okay, do we need to go any further? I don't think so. And in general, fn minus 1 plus f sub n minus 2. It's for n greater than 2. Okay. Each number is a, pardon? Yeah. Okay. So yeah, each number is the sum of the first two. We're still on slide 18. Okay, great. So this one tells us we have a Fibonacci identity. We're going to commute the sum of several shallow diagonals in Pascal's triangle. That was hard to say. Okay, a shallow diagonal for us is like shallow diagonals. Good job. Oh, it smells like coffee in here. No, that's okay. It just smells really good. No, I'm good. Okay, so for example, I gotta figure out where's my, I need this row. Okay, my shallow identity. This is 5, choose 0, right? And then 4, choose 1. 3, choose 2. I think I stop here. Is that right? Is that what's on the thing? Yeah, there's only 3 of them. 5, choose 0, 4, choose 1, and 3, choose 2. Oh, yeah, okay, so I'm okay. So that's my shallow diagonal that we're gonna start with my example for. So we have, if you were referring there, we get, that's 5, choose 0, plus 4, choose 1, plus 3, choose 2. And we know that 5, choose 0 is 1, 4, choose 1 is 4, 3, choose 2 is, yes. And if we add those together, we get what? We get 8, okay. And what does that even tell us? We're looking for a Fibonacci, oh my gosh, Fibonacci number. Okay, so then that Fibonacci numbers are as such. I have it like this. So we get f of 5 plus 1, which is f sub 6, and that is indeed 8. You might have to take it on faith, otherwise we'll be here all day. All right. The Fibonacci identity, I'm missing some letters, is as follows. That's an I. We okay with this? Cool. Okay, so for our example, we had, I think we have I equals 0 to 5. So we had 5 minus 0, choose 0, plus, 5 minus 1, choose 1, plus, I think we only did 3, right? 5 minus 3, choose 3. What would happen if I did another one? 5 minus 4, choose 4. Yeah, which is crazy, right? Yeah, can't do that. Yeah. Okay, so I'm definitely not going to keep going, right?
Yeah, feels like it. 2, choose 3.
I think it's supposed to be 5 minus 2, choose 3.
Yeah,
And that's supposed to be a 3, choose 3. So this, we still have an issue here, right?
5 minus 2, choose 3 was okay. Choose 2 is okay, even more so.
I don't think this is okay. That's a problem. Yeah.
That's a dragon right there. I think we need to hear the dragon.
Okay. I could have done 3 of them. So, okay, so we're not going to include that one. We've been through this before, but it's 1 plus 4 plus 3 is 8. Okay. And we already know that that is also 8. So that's very exciting. Ooh, do I want to submit us to this? Bigger examples. I think we're going to do it. Let's do it for n equals 11.
me guess. That's the lowest one that you go on the Venn diagram in front of us.
Is it really? Yeah, it is. Oh, I guess we could do, what's the other example on the diagram? Is it 8? Let's do n equals 8. Yeah, we'll do it later. That's an 8.
We have 8 choose 0.
Yeah. So we get 8 choose 0 plus. Okay, but in sync.
6 choose 2. 5 choose 3. 4 choose 4.
That's the
And we're in the danger zone.
Okay.
1, 7, probably 15, and then 20, 10.
Yeah, you're right.
1.
17 plus 2 is 19. 32? 34.
What's that? 19, 21, 30. What's 9 plus 7? 21.
Okay, and f of 8 plus 1 is f of, like, not of, but f sub. That is indeed 34. I looked it up. You can believe me. So exciting. Okay, we're doing one more. Let's do n equals 11.
We're getting our rhythm down in the class.
It only took us.
A long time. Okay, what's the first one?
1.
Okay.
Then 11 choose 0. Then 10 choose 1. 9 choose 2. 8 choose 3. 7 choose 4. 6 choose 5. Danger zone. 1. 10.
Something.
It was like 36. 56. 35.
Nice. All right, add them together.
What? Is that 12 squared?
It is. And just for fun, we have, what was our n? 11 plus 1. The 12th Fibonacci number is 144. That's cool. That's super. That doesn't happen, I'm sure, very often. Yeah.
I'm glad we did 11 now.
I'm so glad we did 11. Yeah.
I think it probably doesn't work for
You have to sit and appreciate while it's here.
Yeah. Just like the sun when it comes up in a couple hours.
8.
Okay, yeah. Anyway, so we have I equals 0 to n of n minus I. Choose I is equal to the Fibonacci number plus 1. And I have on my paper, this is not a QED because we didn't prove it, so no QED. Okay, what's next, Michael?
it.
Are you getting tired of the triangle?
So, should we do it again? Oh no. I have to remember how many triangles we need for this one. We need to go to row 6. So we have, oh damn, okay. Now we'll do it in blue. I think we should shake things up. No. Let's do, instead of 1, we'll do the other kind of 1. What's this one?
I think you should start with reciprocal, maybe give us a little bit of room to expand.
Thank you. Do you think you can do it in sync like this?
Yeah, 0 choose 0. 1 choose 0.
Oh shit, yep.
1 choose 1. 2 choose 0.
Damn it.
2 choose 1. 2 choose 2. 3 choose 0. 3 choose 1. 3 choose 2.
Oh, damn it.
3 choose 3.
Damn it.
4 choose 0. 4 choose 1. 4 choose 2. 4 choose 3. 4 choose 4. 5 choose 0. 5 choose 1. 5 choose 2. 5 choose 3. 5 choose 4. 5 choose 5.
One more.
6 choose 0. 6 choose 1. 6 choose 2. 6 choose 3. 6 choose 4. 6 choose 5. 27 pies.
Okay, all that talking makes me need water.
Triangles make hearts.
It was fine.
Okay. What do I have circled here? So where I'm gonna just, oh, I need a different color. You're gonna circle 2 choose 1, and then 3 choose 1. Bless you. 4 choose 2. We should all say that together. 4 choose 3. Oh, I meant the bless you, but you're welcome to. Okay, yeah. All right. I've got some circles around these guys. This is gonna make a hexagon around what's in the middle. Let's just take a quick second and like think about like what do we think is happening? Are there anything that we wonder? Anything we might know? Okay. It's I believe that's 3 choose 2, and definitely not 3 choose 3. Yeah.
I'm not really sure. Like, could we choose epsilon?
Yeah, it's kind of a mess.
Okay, but hold on. If you have 3 and you're choosing an epsilon out of it, how many different? Is it clear you can only find that many ways to do that?
No, I'm saying the numbers up there
Okay, but not if it's 3 choose epsilon, because that could very well be in.
What does it mean to choose by a non-integer number?
Excellent question. When you figure it out, let me know. We'll write a paper.
Like tomorrow. So get on it. Okay. So my thought when I was thinking about this was like, could we add them? Does that do anything? Maybe. I don't know. Yeah, I don't think we're getting anywhere with that. Can we multiply them? Maybe. I don't know.
From each other. What if I just hit the next slide button and see what it's
I think it won't tell you what we need to know. Let's see. What did I end up here? I regret doing this. I regret doing it in this way. I wish I had it here. Do I have this right? Oh no. Oh, I regret so much. Well, we're gonna have to figure it out. Essentially, this is telling us. Now I'm lost. I circled the wrong ones than what's on my paper. Yeah, but I don't want to do that one. Okay. I need to remember, what is this number? That's 2, right?
Yeah.
Okay, what's this one? 3 choose 3, that's 1. Okay, what's this one? 4 choose 2. Okay, and then in a different color, what's 3 choose 1? Oh, whoopsie. That one. And then what's 2 choose 2? And what is 4 choose 3? Yeah, I think so. Yeah, it is. Great. What happens if we multiply those two together? This is 12. What about up here? Wow, that's so crazy. Okay. if we formalize this, we could do some more, but essentially we're, like when we do this, we got this guy here. We're gonna call this row n minus 1. And then we're gonna call this guy, am I missing something if I do this? That was a mistake. This should go this way. So ignore that. And this is gonna be row n, whoops. And that leaves you guys. We'll call this row n plus 1. Does that make sense? Are we okay with that? Okay, and then here we have like a diagonal situation going on here. Oh shoot, that was silly. Okay, sorry guys. This is row n going this way. This is a mess now. This is row n minus, what's happening? N minus 1, n, and then we have n plus 1 here. Okay, and then our diagonals are the k's. So we have k minus 1, and then k, that's this one here, and then we'll call this one k plus 1. And it turns out, whenever we do this, if we multiply like the every other based on its diagonal and its row, we'll get the same number twice. Super fascinating. So based on that, I know this is like impossible to read, and I'm so sorry, but for us, we have, let's see, we end up with n. So like on this one, that was n and k minus 1. So the row n diagonal k minus 1 gives us this guy right here. And then if we multiply that by row n minus 1, so from here, and then I want to pick row k, that's going to give me this guy. N minus 1, choose k. And now we need k plus 1, so that's this diagonal, and n plus 1. And for some reason, they're not adding up, but they should. And we get n plus 1, choose k plus 1. And we're going to set that equal to very similar, but like going the other, every other. So we get n minus 1, choose k minus 1, times n, choose k plus 1, and n plus 1, choose k. And that is our hexagon, right? Hexagon identity. Woohoo! And we can use it, no, we can prove it using binomial coefficients. So friendly reminder, that was n choose k is equal to n factorial, k factorial, and then I think it's n minus k, yeah. Okay, it's a doozy. What were you gonna say? Okay. We could do that too. Yeah. Just use all of our identities.
Minus 1, choose minus 1 minus k. If you're doing the.
Okay. Yeah. Okay. So we'll do this bit by bit because it's. This is this, and we do k minus 1. That's a divide sign, factorial. And this is n minus k, factorial. Oh, this is gonna suck. I think we can do it. This is n minus 1 factorial, and then this is k factorial, n minus k factorial, woohoo! And this is n plus 1. I think there should be a negative 1 here, right? N minus 1 minus k, yep. And this is going to be k plus 1 factorial, right, times n plus 1 minus k plus 1 factorial. Am I on the right track here? Yeah, we'll get to that. Oh, sure. Yeah, so it goes like that. Okay, cool. And then this is n minus 1 factorial, and it's k minus 1 factorial. Choose, where am I? N minus 1 minus k minus 1 factorial. We're gonna run out of room. And then we'll do this one down here. So this is n factorial over k plus 1 factorial. And then n minus k plus 1 factorial. And then one more. N plus 1 factorial over k factorial times n plus 1 minus k factorial. Good enough.
But you should put a question mark top there. You don't know that one. But after that, I feel like we're okay.
I mean, maybe fill it in with a bunch of double head.
Dots. You know,
Yeah. Yep.
and wrap it around. So we made it.
So let's see.
At least not
Yeah, plus probably 10, I'm thinking. Okay, cool. Thank you. Where are we now? Oh no. All right, let's try another one. Hold on while I erase this. And then Michael, what time, like what's
We're
the,
at 6 o'clock.
what does that mean?
That means that you have half an hour more by the book and up to an hour more if you want.
Okay. I don't know how that's gonna go.
You want me to go touch base with Nannah and see how she's feeling?
Probably not you, because you're there. But I think it's for sure probably about a half hour. But I'm not, maybe more. Yeah. Okay. Sorry you're gonna miss out on this because it's super exciting. So we have this definition of capital N of A. That's gonna be the number of times a number A, which is greater than 1, appears in Pascal's. I like it better. Pascal's triangle. So why should A be greater than 1?
Because if A is less than 1, it doesn't appear in the triangle.
Okay, let me ask again, a different way. Why is A strictly greater than 1? Awesome.
It appears a lot.
Yeah, exactly. Both of those reasons are what I was looking for. Okay, so for example, I'm just going to say this really quick, off the record. When books and proofs say it's not hard to check, it drives me crazy. It's like, thanks for rubbing it in. So n of 2, so the number 2 is going to show up one time. Where is it show up? And we never see it again, right? Why? Yeah, we're getting bigger and bigger and bigger. Yeah, great. Okay, so that shows up once. No, not A. N of 2 is 1.
And the next row is going to be 3.
Okay, so the next row is 1, 3, 3, 1. So how many times do we see 3? Twice. So N of 3 is exactly 2. And then the next one is 1, 4, 6, 4, 1. So we see 4 twice also. To catch you up, it's the amount of times that this number shows up in the triangle. And then also N of 5, if we were to do the next one, is also equal to 2. So something that's kind of interesting, and you can read it on the slide, is if we were to keep doing this triangle until like next year's Pi Day, and we arrived at a line that had 3003, that actually shows that number shows up 8 times. Isn't that crazy? Yeah.
Same line.
Because 3 zeros and 3 can have both like 8 twins. Like the number.
Yeah, sure. Yeah. Okay. Okay. No worries. Oh, okay. So, can I see what the next slide is? I forgot. Oh, okay. Awesome. So there's this really cool conjecture. It's still an open thing. Master's conjecture says there exists a constant C such that N of A is less than C for all A greater than 1. Yeah, like a maximum bound. However, it's a conjecture. We don't know that for sure. That's what I'm, like doing on my at my day job. That's not true. Yeah, right? Crazy. Okay, but I have some other fun facts about Singmester's conjecture. So a fun fact, all odds appear twice. So that's cool. You actually mentioned that earlier, I think.
At least twice.
I think it's at least twice, yeah. 6 appears 3 times, that's pretty cool. And in fact, every central binomial coefficient appears 3 times except for 1 and 2. And all numbers of the form P choose 2 for prime greater than 3, these all show up 4 times. And there's infinitely many numbers that show up exactly 6 times. And the smallest number to occur 6 times or more that we currently know is this one. The next smallest, like they found this one and they're working on the next one. So maybe it should be the next largest. I don't know. I could keep going. It's this long.
A little bit better.
Does that work? Sorry, 6 or more times. Yeah, I think I'm confused by that. But they're working on finding out more, that like the next number that occurs more times. Okay. I'm confused by it too, but it's I think maybe. Yeah. Yeah. Maybe. I found that like a little bit ago, so take it with a grain of salt, and I can look it up later. Okay, what's next? This is cool. What's next? Okay. Where are we? Okay. I think we've seen this today already, right? But I don't remember, but I feel like we saw it. Okay, binomial theorem. That's a sum. Okay, so we have this binomial, x plus y to the power of n, and it turns out that's equal to n choose k, and we're summing over k, x to the power of k, y to the n minus k. And these can kind of flip-flop, because it could be like y plus x. Are we okay with that? Okay. Pardon? Yes, addition does commute. Okay, we're going to prove it. On the left-hand side, we have, well, we have it, but I'll write it again. X plus y to the n. And for example, if this was like squared, we'd get x squared plus 2xy plus y squared. Cool. Okay. I'm going to do that example actually for fun. Here we go. Okay. If we look a little closer, this is 1x squared plus obviously 2xy plus 1y squared. And if I were to do this one instead, x plus y cubed, I would get 1x cubed plus 3xy, and that's squared, plus, okay, we're done with that, 3xy squared plus y cubed. So this is a 1, a 3, and a 1, and a 1, a 2, and a 1. What does this look like to you guys? Wow, that's so cool. Okay, yeah, so it looks like this. So this row here is 1, 2, 1, and this one is 1, 3, 3, 1. Very exciting. Assuming based on this, if I put a 4 here, you could probably make an educated guess on what would be next. Yeah, with some variables attached to it. Yeah, great.
This is why they're all binomial coefficients.
Okay, I have another example, but I feel like you guys don't need it. So why does this work? We're gonna show it with induction. So we're gonna do this, and I'm gonna go with my base case of what do you think you want it to be? I'm gonna go with 1.
I mean,
If it was 0, what would I have over here? Yeah.
times.
Yeah.
Yeah, I guess you raise every x and y to the 0th power.
Okay,
Do we want to do it?
no. I was talking to Mark about this. When you choose something that's larger than what it is, it's 0. Right?
Mhm.
So I guess, yeah, I would choose 0.
Yeah.
Yeah. I mean, we could do it for fun. Okay. Okay.
0, so they're gonna go away, so we're just gonna get a 1 out of the field.
Oh, I think we messed
So
it
I
up.
think
Yeah,
that-
I think it's 0.
It does work.
Yeah, because x plus y to the 0 is 1.
Mhm.
Which is
And that's 1, right? And 1 and 1. Well, I'm still gonna do it with 1. Yeah. Yeah, nice job, guys. We're gonna do 2 base cases. So we have this. Yeah, okay, that's fair. Yeah.
Strong induction.
Yeah. N equals 1, right? Yeah, so then I have 1 to 0, x to the, okay, so that's 0, y to the, what's n, 1 minus 0. What do I end up with? Why did that happen? Thank you. Okay, I have this, and then n was, what are we at? 1 minus 0, right? Does that make sense? Thank you. Okay, so 1 choose 0 is, okay, x to the power of 0 is, y to the power of 1 is, okay, plus 1 choose 1 is, x to the power of 1 is, that's a 0, y to the power of 0 is, these are,
Absolute value that.
thank you. So we end up with y plus x, right? And we have y plus x. So the base case number 2 works. Do we want to do a third base case? I don't either. Okay. Did you say why not? No.
In 2 cases, so what's the third, you know?
You want to do like 10 cases? We got all day. Yeah.
With the triangle?
I don't know.
I think the proof really just comes from telling you the definition of the choose one.
What's happening? That's a k. X, k, y, n minus k holds. Ooh. Okay. We want to show it works for n plus 1. Anyone else getting hungry? No, I'm okay. Is there any cold pizza back there? Can I read my handwriting? That's a K, right? Yeah. I think it's a K.
Kind of feel.
Feels like a K to me. Yeah. Okay. And this is n is n plus 1 minus k. Okay. Okay, and then over here we have x plus y times power of 1, x plus y, power of n. Is that okay with everyone? And over here we have the sum from k equals 0 to n plus 1. These should technically all be m's. But that's okay. It doesn't matter. Yeah. I mean, like, I always feel like you're supposed to want to show it, and then you show it with a different variable, and it's fine. But, yeah. What do I have now? X to the power of k. And then I have one of these. And I think I have one of these, right? And then I have one of these. Does that work? Am I going a little crazy here? Awesome. Okay, let's rewrite the left-hand side in summation form. So we get k equals 0 to n, and this is m plus 1, choose k, x to the k, y to the m minus k. Does that work? I think I'm, oh, times x plus y. Okay, that's better. That one, that one. Okay. That's an n. I don't think I changed anything on this one. So we'll just keep going. Okay. And if we plug x and y into this summation, we end up with is that right? Yeah, we get this. Where? Yeah, it's right there, isn't it? Why did, okay, that works. Yep. Plus another sum of k equals 0 to n of n, choose k, x to the k plus 1, y to the n minus k. And I believe that this worked. I don't know why I believe that. Just kidding. We have a long way to go. Okay, so next what we're going to do on this side is we're going to take out a factor here, and then we'll take out a factor here. And we could do a lot of things. And I don't know if we want to keep going. I feel like not doing this anymore. Not doing this bit. I want to keep doing this. Yeah. Anyway, we take out a factor, and we end up with n choose 0 over here, and x to the power of 0, and then y n plus 1 minus 0, plus n, choose n, and that's it. And then x to the, y to the n minus n plus 1 minus 1, so that goes away. And then same with the, no, then y goes n plus 1 minus 1 plus 1, so it's just y. And then we end up with the sum from k to 1, k1 to n of n choose k, x to the k, y to the n plus 1, plus the sum of k equals 1 to n, n choose k minus 1. And we keep going, and it gets really cool. And then we use Pascal's identity, and we combine some things, and the right-hand side and the left-hand side end up working. And the proof is left to the reader. Yeah, so in case you're following along at home, we did that on the board. Mm-hmm. Yeah, it was like a 25-second delay. Wow, I can, yay. We'll just go ... QED. And that's probably worth 20. Yeah. Probably worth like 20, choose 10, actually. Yeah. Oh, okay, that works too. I don't know, we'll just go with it. Well, it's worth 6, choose 2. Okay. Oof. Anyone else getting like a little tired? Mhm. Okay, hold on.
Do you have wings yet?
And
Dragon.
you need to do that in front of the camera for the sponsor.
Oh, we have the dragon count. Yeah.
Okay, are we on 23? We are. Pardon? That's so exciting.
So, are we going to 6:30 or?
We're going to
I think we're gonna go until
If I need to go find people, I can go find.
I have 2 that I really want to do. And I think this one's not gonna be horrendous. Yeah, so I think maybe 20 minutes. Yeah.
That would be good. And then we can do it like a sentence.
Yeah. We can all go outside and watch the sunrise. And as it rises, we can chant our Pascal's triangle.
Yeah.
Okay. Oh, this is just a problem. We don't have to prove anything. What happened last year? Oh, okay. They can't hear, I promise. No. Okay, so we have this problem. Pick, that's an X. X and Y greater than 0. You have a bias coin. What's a bias coin?
the one that I use.
Oh, my back hurts. Okay, so which is heads? What's happening? You have a, thank you. Find the probability of getting exactly K heads on N flips and use this to prove binomial theorem. Can we do it?
Binomial
Yeah.
distribution.
Great. Okay, so we let P be the probability of something. I'm gonna go with that. Prob, that works. Of heads. That's so much worse. P-R-O-B? That's a B? Yeah. What did I say this was? Of heads. Okay, great. So then, if that's the case, the probability you get tails is what? You guys are so great. Is, what do we call that? P minus 1 minus P. Okay. So the probability I get heads is in the first K flips, and tails every other time is P, K, 1 minus P, N minus K. For any positive integer K. No, that's not what I meant to say. Yeah, for any possible K, we get, I should label this. Well, that's next. But I'm gonna keep going and we'll see what happens. Is that okay with you? Okay. No, I won't ignore you. Oh. Yeah, just keep swimming. Okay. Our possibilities, we have a coin. We either have all heads, which is, yeah, and then no heads, which is the same as all tails, or an N amount of heads. Okay? So then this is going to be all the possibilities to get heads. That's a heads, yeah, which is equal to 1. So then from the problem statement, we get that P is equal to x over x plus 1, right? Okay. And we know P is greater than 1 and x and y are greater than 0. So if that, then we have P equals x plus y greater than 1. Okay? So now we're going to plug in this to our formula up here. So we're going to end up with, this is k equals 0 to n of n choose k. I have a p here, so we'll go x. I can't read my own handwriting, that's a y. X plus y to the power k. And then this is going to be 1 minus x over x plus y n minus k. Okay? And now we're going to just do some like algebra stuff, and we get this again. Oh yeah, this is my fancy one. No? Adding fractions with unlike denominators? Oh, yeah. Okay. Okay, so then we get that, and this simplifies down to something, and I'll get there in a second. And then we can distribute this in here. So if we do that, so like this, this distributes, and then we figure that out, and we get k equals 0 to n, and choose k, excuse me, 1 over, I feel bad that I'm kind of like hand waving this step here, but it all works. X plus y n, x to the k, y n minus k, and that equals 1. Do we understand this? Should I do some more?
Oh, did the n and the k both of those cancel or something?
Yeah, there was some distributing and some canceling and then some adding or subtracting. Okay, are we happy with that? Okay. So then x plus y to the n is not dependent on k. So if we multiply both sides by x plus y to the n, we're okay. Okay? So we get, if we do that, we get, this is a 0, that's an n, this is n, choose k, x to the k, y to the n minus k. Feel pretty good about that one? Yeah? Hannah is, because we multiplied this by, we got rid of it. Okay. What do you think?
200.
All right. Okay. Yay. Where are we? 23? Can you go to the next one? I have 2 more. Okay, so as the slide says, the binomial theorem has many uses. First application allows us to quickly find the coefficients of in binomial expansions, which we kind of talked about. So we can use the binomial theorem to expand x plus y to the 4th, and this one's kind of fun, x plus 2y to the 3rd. This will be pretty quick. I think we can do it. Let me get a marker real quick.
4, 1, 1,
Hold on.
3, 3, 1.
I think we had a full participation on that.
All right, ready? It's 1, 4, 6, 4, 1.
What goes here?
X,
Okay, what goes here?
Y,
What goes here?
X squared, Y squared,
What goes here?
X, Y cubed,
Yeah.
I.
Nice job.
Plus sign.
Okay, there and there and there and there. All right, let's do this one.
1,
Okay.
3, 1.
What goes here?
X cubed,
Mhm.
X squared, Y. X squared 2Y.
Oh no, is that just 6?
So those 3's become 6s.
This is gonna be.
Oh no, because
So we have
okay,
x.
X 2Y squared.
Oh, there's to be pluses here, right? Yeah. Okay.
Now it's 2Y cubed.
We didn't use the binomial theorem. Well, did we? We did. We did. Yeah, we're good. Yeah. We didn't do it like aggressively, you know, with this and this and this and then like this and that. We, you know, but it's fine. We did it. It's totally there. Yeah. Yeah. You guys are ahead of the curriculum. Okay, I feel pretty good about that. What's next? Oh, gosh. Okay. I think we did one of these already, right? Oh, right. Okay. Okay, A is that one. We got this. All right. Friendly reminder. Do you guys want binomial? I'm gonna write it right here. You don't get to reply. Here. N equals. I can't believe how long I've been awake. Is anyone else starting to feel that? Not quite, but like, actually, yeah, my alarm goes off at 6:30 every morning. That's insane. Oh boy. Actually, I really hope my alarm isn't about to go off. Anyone else's alarm is about to go off? Okay, so that's a binomial theorem. Let's, oh, sorry, what? Okay. Let's rewrite 2n as a binomial. Is that what I want? I can do 1 and 1, thank you. Yeah, I can, yep. I had like an intermediate step in here. We don't need that, we're so good. So we'll do, this is, I really wish I would have switched these. Okay, I feel better now. 1 plus 1 to the n equals the sum from k equals 0 to n. And choose k. All right, what's my x? To the power of, what's my y? To the power of, awesome. Okay, and what does this equal? Because that's 1, and that's 1, and 1 times 1 is awesome. So then we're done, right? I think like, so I'm gonna say that that's 3003 QEDs, which unfortunately only appears 8 times. So I think it's 8. Yeah. Okay. So the next one, part B. I'm gonna go like this: 3n sum. Now I wish I would have done it the other way. Oh gosh, okay.
There's the bell. There's class.
6:30.
I have so many equal signs up here. I just need the one. Okay. So we rewrite, I'm lost. Yeah, so we rewrite 3 as a binomial. 2 plus 1. What if we did 1 plus 2? What would, yeah, we can do that. I think we should do 2 plus 1 though. Okay, so we do 2 plus 1 to the power of n is equal to this, k equals 0, n choose k. What's my x? What do I raise it to the power of? What's my y? What do I raise it to the power of? Awesome. Okay, so I get the sum of k equals 0 to n of n choose k. 2k. What's 1 times that? Awesome, so I'm just gonna leave it there, and I think we're okay. Awesome, so probably 10,000. Okay. I just don't think so just too big a number. Can't do it. Yeah.
But it's not really any different from 3, so.
Yeah. Yeah, you're into infinity.
So we rewrite 0 as a binomial.
How about 0 plus 0?
Yeah.
1 minus.
I like that better. Yeah. I'm gonna go -1 plus 1 just for fun. Shake things up. Okay. And then this is what? We got this is that, and this is that. Wait. What's happening?
Flip-flopped.
I think I did too. Is that okay? That doesn't matter. Yeah. Okay. But I want that to be x, right? But the good news is it is. So I'm just gonna do that. Is that okay with you? Okay, and then I want like a y in there somehow, right? Mm-hmm. Cool. Love it. And then here, I'll put this here. And then what's that equal to? Because 0 to the power of n is. Woo, woo, woo. So
Next time you
QED
add
one.
0 to there you go.
That one's done. What's the next one, Michael?
This one.
All right, we're gonna do it. And I just need like a pep talk. I finished.
You're the best mathematician I know.
That's so sweet. I was about to give you guys a pep talk.
Like 3 minutes. You couldn't figure this one out.
Yeah, it's good. So during, I want to say it was, you're not Anna, Hannah's proof. Me and Junwei and Michael were trying to figure this one out, and it turns out I made a sloppy mistake, and that's why we couldn't do it. So the pep talk is, we can do this, and I believe in us, and we'll all get extra credit when we get it right. And a finite amount.
And Math Prof English in the chat says woo. You can do this.
Like, is it like this?
Yeah.
Okay, so, like, I think we need to be minusing zeros here. So this, yeah, I like it. Okay. Fun fact in life, the number e, which is a number, is equal to the limit as n goes big of 1 plus 1 over n to the power of n. This is a super cool thing. Yeah. We're going to use the binomial theorem to show that e is also equal to, that's not what I need. here. I almost wrote a K. 1 over K factorial. Okay, cool, cool, cool. And for my own ability to think, we're going to rewrite the binomial theorem here. Unfortunately, I had it here and I erased it 2 seconds ago. Yeah, I'll just leave it there forever. Okay, cool. That belongs there now. So over here, we're going to have the limit as n goes to infinity of that. And this is going to be equal to, thank you. Oh yeah, we're putting it, we're doing this. Okay, great. Of n choose k. And then my x is 1. So 1k, and my y is 1 over n minus k. 1k is this 1. Cool. So then I'm going to just go like this. And then we get, yep, okay. Then we get this. This is where I made the mistake earlier, if you're interested. We get 1 over n to the n minus k. We don't get 1 to the n to the minus k. That was a mistake I made. Okay, so then this is cool, and we get this of n, because we got that guy, and it's k, n minus k, and that's equal to 1 over n to the, yep, n minus k, okay? And then we're just going to do a little bit of expansion here. This is n to the n, or times n minus 1 times n minus 2 times n minus k times n minus k minus 1, and that's all there. And then this is all over k factorial, which is good. We want that. N minus k factorial. So this here, that helps us get rid of some stuff, right? So all of this, right? That's gone. Okay, exciting. All right, awesome. So now we're left with pretty much just this. Okay. And then we're going to do a really fun trick, and this is by... I do. Thank you. Okay, but we're going to get rid of it so soon. Yeah, so soon. So I'm going to write this here. By Tannery's theorem, there's, by the way, this limit is all, we've had the limit as n goes to infinity the whole time. So this is here. And this theorem tells us that because, why can we do this? I don't quite remember, but we can switch these.
Ooh, limits and sums are interchangeable. Isn't that just like the linearity of limits?
Sure. Yeah. Okay, so we get this. Of this stuff. Also, we can pull out a 1 over k factorial right here. Okay? And down here, I am left with n to the n minus k. So n's going to infinity by that beautiful description of my notation here. So if n goes to infinity, this is getting really big on top, right? And this is getting really big on the bottom. Yeah, nice. So this side equals 1. Okay? Awesome. Okay, so then we're left with, this is like, goodbye. And we're left with, oh, my knees. Wow. K equals 0 to infinity of 1 over k factorial. And I think that's exciting. Yeah. Ooh. So I'm going to go with plus e. Yeah. It's like 2.1-ish. Or is it 2.71? Well, if we're going to do that, we might as well round up to 3.14. Okay, remember when I was like, hey, I have a note here to not panic when I get to slide 27? Where did...
At some point.
No. Now we get to panic.
You have minus k factors on top, right? That's in the text.
N minus k factors on top. And
I thought it was just like series.
No, we do have the n minus k factors up top, I believe. Yeah.
Ah, I think
Yeah, sorry. There's dots, dots, dots here. Yeah. No, you're good. Okay, I found slide 27, so no need to panic. Have you found people?
Yeah, it is. Are you ready?
No, I have one more. I just don't believe you.
Oh, he's in the hall.
Oh, okay. I was like, you just pointed to an empty chair. Like, is that the chairperson? Okay, one more. Woo, and we can do it. Okay, I need this again. I don't know why I keep erasing it. You'd think. Oh no.
I think we could do it.
I think we can do it. Yeah.
sum k equals 1 to n.
Is that right? Yeah, nice job, guys. Okay, so we have a derivative, and it equals this limit. If you were in calculus one day in your life, we're going to use the binomial theorem to show that the derivative of the function x to the n is x to the n. This. The derivative of this is n x to the n minus 1. Power rule. Yeah. Cool. Okay, so binomial theorem says this, yay. And we know that this, I think I'm going to start over here. There's an n in there. Are we going to infinity? No, we're going to 0. We know that from life. Okay, so I think we should take a moment and reflect on the fact that we for sure have a binomial coefficient in here somewhere. That's pretty exciting. Great. Okay, so that being said, we can now do this. So we get this limit as n goes to not infinity, like almost quite the opposite. K equals 0, n choose k, x to the k, h to the n minus k. That's a k. And then we got minus x to the n, and it's all over h. Okay, if we think back to
0.23, that it's h that goes to 0, not n.
You are correct. It's just like it's growing. It's like a baby, and now it's. I think. Yeah, I think that's not something that I can really fix. And as someone with 3 N's and an H in my name, I feel your pain. Yeah. Awesome. Sometimes people spell my name like your name with a taller H. Okay, where was I? Oh, if we think back to calculus years, if we take the limit right now, what issue would we have?
Zeros.
We'd have 0 issues?
Dividing by 0.
Yeah, because we plug this in, not great. Can't.
Those are big.
Big issues.
Really big.
Yeah, they're definitely not 0 issues, but they are 0 issues. Okay, so then we want to get rid of the denominator. And to do that, we're going to get creative with our x to the n situation. So let's absorb our x to the n in here. Does that work? Absorb is probably a bad term to use, but it's how I think of it. So then we're going to do it. I already did that, and I did that. We're going to do this. I have a feeling this limit should be here. N to the n. Yep, I think. So we're just gonna note that this equals this, okay? That's what that is. Right, because this is the n minus n, that's 0, that goes away, and we just have this. Okay? Okay, cool. So I make sure we're okay with that. So then using this, we get the limit as h goes to 0 of sum k equals 0 to n minus 1 of n choose k, x to the k, h to the n minus k, plus x to the n minus x to the n, all over h. I feel like I have to make sure that that was okay. I think it's okay. Okay. This is an x. Those go away. Okay, moving on. Then we have the limit as h goes to 0 of, pull this h right here. And we have the sum from k equals 0 to n minus 1 of n choose k, x to the k. This is blending, but it'll be okay. H to the n minus k minus 1. And this is all over h. So what I did is I took an h out. Okay? It's hard to tell with what's going on right here. N minus k minus 1. So I pulled one out of here. Okay? So goodbye. And now we have, and I just did that again here. Now we can take the limit. So everything with an h is going to go to 0. Okay? So we have the sum from k equals 0 to n minus 1 of n choose k. I think that's a k, right? Yeah. X to the k, h to the, thank you, I can't read my handwriting anymore. I have a concern that we're multiplying by a 0. Are we going to be okay? Yeah. Why did I had this concern earlier. And I think but if that is 0, then that
Those are k to n minus 1, so you have h to the n minus 1.
yeah.
H to the 0, so it's still okay.
Okay, so I'm going to do that again. So this was n minus k minus 1. And we can rearrange this as n minus 1 times n minus 1, right?
You have to reduce the power of h by 1 when you got rid of the denominator.
I think minus 1 that would work.
Here? Okay. If that's not correct, that's okay. Okay, so by switching this, now Yeah. I don't know. I feel like it shouldn't be.
The only term without a H is when K is minus 1.
Every other term is still gonna have an H, so we can just as well assume.
And then that's what we want.
Okay. Can you say it louder?
In the chat, SantaFam023 said the only term without a H is when K is n minus 1.
Ah,
So
that's where that comes from. Okay, cool. Awesome. Okay, so that's good. And then we have, where am I? I'm here. Sum from K equals 0. Thanks, Santa Claus. Who was that? Not Santa Claus. Okay, x to the n. And then h is gone, right? Yeah. No? I feel like it is. Okay, we're going to keep going over here. We ran out of room. So now we're going to use one of the identities we learned earlier, and we get k equals 0 to 1. And this is the same thing as if I were to write n to the, choose n minus 1, x to the n, and then, and I think I'm going from to n minus 1. Yeah, that works. That's why that happened. What was that, Anna? Okay. I think because this is now n minus 1, maybe that's why it's better. I've totally lost track. But anyway, no.
Well, the only non-zero term is when K equals n minus 1. So
the
sum we don't need a sum.
yeah, the sum goes away, and then you only have a K.
Yeah.
Put
All
in.
the terms have a factor of 0 except when K is n minus 1.
Bingo.
That's how it works.
Okay, so this is gone. No.
That's how we have n choose K.
Yeah. Yeah. Well, so
n minus 1 is the only one that's not 0.
yeah. You're saying that here?
Yeah, does that need to be that?
Well, I feel like it should be k, and then it becomes n minus 1, but that doesn't seem right either. No? Yeah. Oh, okay.
No.
Yeah, yeah.
Yeah, we need
But it should be an x to the n minus 1.
But that's just the typo, right? That's all
Yeah.
over there. That's -1. Yeah.
Yeah, there you go.
That's the theorem. What's n choose n?
Oh, duh, because we want this. Yeah. Because, yeah. Okay, great. So then we have this, and that's great. QET. And so that one was probably worth, we had a team effort of 1, 2, 3, 4, 5, 6 plus Santa Fe. So I'm going to go 700.
Yeah.
Okay.
Santa Fam and math prof English.
Okay. I wrote 7. So probably actually 70,000 in one because I don't want to erase the 0. Okay. Awesome. Are we done? I think we're done. Yay. That was a long couple hours. One more thing before I am actually done. We should probably figure out the actual QED count. So what are we at? Yeah, but there were more because we had 7,000 for that one. We had 3,003 at one point. We had 20. So I think the whole count for Nannah, I'm going to go with that. Yeah. Okay, thank you. Again? No. No. Okay, are we on break?